And here we go. All right. So we were just doing all this stuff, and yeah, I think I want to. The thing I wanted to draw your attention to is that here's the result that's been giving us all this success. Okay, so the refractive index. And so I want to retrace my steps back to it. And I want to actually plot this, because that's where we will learn that, I mean, you can clearly see that there is something unphysical about this, that when omega equals omega naught, when you're on resonance, you get infinity. I mean, that's just bullshit. So we want to fix this. And that's where this concept of line width is going to come in. So I'm going to, when I post these lecture notes, remember we had this page 4, and there was another typed thing that went with it, which I will number. Also, when one general thing I want to say is that, and usually people are good about it, but when I ask you something in a quiz, then, and if you are not sure about it, don't go Googling around, because at this point, Google is not all that reliable, for this course and for 600 level stuff and all. So stick with what we're talking about in the notes. If you can't find it, then look at the video lecture, and find it there. And if you still can't see it, just ask me. But anyway, so that's your refractive index. And what I want to do is plot it. Okay, so let's see what we get. So I'm going to, here's the formula, and this is 05, 05, 25. And what this is that, and I believe I may have, sorry. What we're talking about is that introduction to concept of line width, spectral line width. Okay, so let's just examine this formula. So n, the refractive index, is equal to square root 1 plus n e squared over m epsilon naught 1 over, and just tell me when it's 345, okay? Alright, so I got this. Now, what I want to do is, because in the end I'm interested in lasers and stuff, so in the context of lasers, okay, one thing that you would appreciate is that for gases, obviously, so maybe that's the first thing, for gases, okay, and by the way, when I'm in this mode, I cannot see comments. So, if you have a question, you'll have to probably speak up or something. And that's a disadvantage of this document camera approach. Anyway, for gases, the refractive index is always about 1, right? And what that means is that, one other thing, just to make this more compact, the e squared over m and this, we have shown in the past is just alpha. Okay, so this is written as square root 1 plus n alpha over epsilon naught. Okay, yeah. And for gases, this is about 1, which means that what it's saying is that your this means that this part is small, and so you can write n as approximately equal to, you can do a binomial approximation, right? What is the binomial approximation? 1 plus x to the power n, and if x is much, much smaller than 1, is simply 1 plus n times x, right? And that takes away the square root, which is nice, because then this just becomes 1 plus n alpha over 2 epsilon naught, okay? And it's easy to plot and stuff, okay? Now you might think that, well, this doesn't really apply to lasers, but it's interesting that, you know, we've already talked about, well, gas lasers, clearly, you know, gas lasers, we're done. I mean, like, we can use this approximation, okay? But you've seen that for liquid, you know, like dye lasers and solid state lasers even, we've already considered these cases where the solid state lasers, you know, ruby, remember it was the chromium ion concentration that matters, right? For the ND-YAG, now who was the dopant in ND-YAG? Oh, the neodymium. So neodymium ion concentration, right? For dye lasers, it turns out that as Ben, no, not Ben, but maybe as Scott would tell you, that you take a small amount of dye, mix it in a huge amount of ethylene glycol, you know, and that, so the dye itself is very tiny, like small amount of dye, you know, just like milligrams, and that's what sustains the entire dye laser. So the point is that it's always just the, you know, in this case, it's a small dopant concentration. And we already have seen that the dopant concentration is less than air, you know, or about the density of air. So actually, for lasers, this approximation works. The refractive index is indeed about 1, surprisingly, for dye lasers, solid state lasers, for all these lasers, okay? So you can use this approximation. And so then the refractive index, therefore, is 1 plus n, so now the square root is gone, ne squared over 2 epsilon naught, okay, ne squared over n, 2 epsilon naught, and then 1, and this is easy to plot, okay? So we can plot it. Now let me remove this. And you know what you see. Okay, so let me plot n as a function of omega minus 1. So I'm just subtracting the 1. And so let's say this is omega naught. This is omega, right? Let's say this is 0. And so you notice that for, I mean, remember, this is a small quantity. Like this entire thing is small. And it only becomes significant when in the vicinity of where omega and omega naught are about equal. Shoot, did I record? Did I press record here? Yes, I did. Okay. All right. So what happens is, and notice that when omega is less than omega naught, so on this side, this is 1 plus something, but when omega is less than omega naught, then this whole thing becomes negative. So basically the graph would look like it's close to 0 on the positive side, and then it starts to go up at omega naught, and when omega is larger than omega naught, then this thing is 1 minus something, right? The 1 has been shifted over into the end, so it's 0 minus something, so it does this, and then it starts to, and then for omega equals omega naught, it blows up. Unphysical, totally unphysical. Okay, so that's the thing that you get. And I want to, get rid of this unphysicality. So, so here's the thing that I will do, and this sets me up for, so get rid of the unphysicality. Unphysical just means that it's just stupid. It's not real. Get rid of unphysicality in the solution. And you know where this unphysicality in solution? By introducing into the Lorentz model. And physicists always like to think simple because they're dealing with complicated stuff. I mean, the experiments sometimes can be, look, all scientists deal with complicated stuff. Biologists often do not have the choice. Like if someone has a brain tumor, you can't just approximate it as a sphere inside dough or something. No, you have to understand what all things, any little thing goes wrong and the person dies. So they have to sort of keep track of all the little details. But physicists tend to go after like the deep, fundamental, sort of universal truths, and so they simplifications. And they like simple solutions as long as a simple solution can work. So anyway, Lorentz model is a simple solution, and I want to get rid of this. Oh, it's 3:46. I'm going to just take like 3-4 minutes more. I want to get rid of the unphysicality in the solution by introducing into the Lorentz model the concept of, and there's one word I'm going to write here, and I just want to bring out the Lorentz model for us to look at, so that it becomes clear what it is that I'm wanting to do. And here, I've lost my Lorentz model. Just give me a sec. It's here somewhere. Now, here's the mass on the spring going back and forth, right? And we wrote the equation for this in this way. There was the restoring force from the spring, and there's the driving force. Now, think of a real mass on a spring, okay? What have we neglected in this problem? Because the solution that we have would apply to a mass on a spring, right? But there is something we neglected, and that's why we got that unphysical solution, this guy here. That's why we got this thing blowing up at, like, what are we neglecting here? The mass on the spring. Is there something real world that we have not included in our model? Like,
Friction.
Friction, exactly. So I have to now introduce into this the concept of friction. And of course, friction is a multi-splendored word here now, right? Because what does friction mean, in the context of, friction in the context of light atom interaction. Okay, and so it'll turn out that what it means is things like spontaneous emission is one source of friction. And of course, it's not friction as in what you think of things rubbing against each other, but it has a very similar effect to friction. Collisions have a very similar effect. Okay, so it's a bit like, it's a multi-splendored word, this friction, and we're going to stretch it to include effects like this, which will then lead us to effects such as Doppler broadening, the Doppler broadened line width, which we'll talk about. It will also lead us to the natural line width, which I have discussed before. This comes from spontaneous emission, the natural line width. Um, and okay, so there's also something called the power broadened line width. And so these are things that we actually measure in the lab. Okay, but anyway, so that's what I need to talk about. I'm going to put in friction in the Lorentz model and show you what happens to the curve. And what you'll notice is that this delta function will become a smooth function, and that's the line width that we're talking about. Okay, so anyway, I guess we shall discuss this next time. I've exceeded my brief, taken way more of your time than I intended to, so I'm going to stop, and let me stop the recording first.